Okay, well, good afternoon, everyone. Thank you for coming. It's a great pleasure to have here today Professor José Moura from Carnegie Mellon University from the Electrical and Computer Engineering Department. And Professor Moura, of course, is well known for those of you who are in the area of signal processing and controls. And he's currently the Philip and Marcia Dowd University Professor at CMU. He's got a wide array of interests, and in particular signal processing and data science. In fact, he has this provocative title today, Data Science with a Signal Processing Viewpoint or Approach. He's the current VP for Technical Activities for IEEE. He was the IEEE board, on the IEEE board director, president of the SP Society, as well as the editor-in-chief of the Transaction on Signal Processing. He also got, for his achievements, he got the Technical Achievement Award, which is a fairly high and prestigious award in the Signal Processing Society. He's a fellow of the IEEE and AAS, and a corresponding member of the Academy of Sciences of Portugal, fellow of the U.S. National Academy of Innovation, and member of the U.S. National Academy of Engineering. And it's a pleasure to have him here talk to us about data science, a new approach, or a novel approach. And thank you for coming. The floor is yours.
Thank you very much for the nice introduction. And please interrupt whenever you feel that you have a question. So I don't know if it's a signal processing approach. Now that you commented on the title, maybe I should say data science equal signal processing. That would be my perspective. But anyway, let me just make sure that I acknowledge the sponsorship of the Air Force. Okay, so I want to, the first few minutes, I want to contrast what I mean by data science with another area that is pretty new, which goes more maybe by the name of network science. And so for I taught a course for several years at CMU on network science, thinking that I was actually that it was very similar to what I was doing, but I really looked at the subject and didn't exactly seem like. So I won't, and over the years I kind of start distinguishing between the two, and so I want to give you a little bit of contrast between these two terms. So the network science, you go to the source of knowledge, current knowledge, which is Wikipedia, and you see from there that network science is complex networks, and then gives examples, telecom, computer, biological, and so forth. Things like graph theory, coming from statistical mechanics, because the physicists really were the ones that in the maybe late 90s and 2000s, they put forward a lot of the work on this. And social structure, I'll come to this. Okay, so that's more or less what network science is. Now you go to the same source of wisdom, Wikipedia, and you see what do they say about data science. It doesn't seem very different, but anyway, extraction of knowledge from data. Mathematics, statistics, signal processing, maybe, Hamid, did you go to the page and add that term? Data engineering, pattern recognition, learning, blah, blah, blah. And then it comes with the words big data. So it seems that one is network-driven and the other maybe is big data-driven. Okay. I don't want to say exactly this, but here is an example of what I interpret. So when you are doing the network science, basically you come up with some, from the data that you are given, from the description of the problem, and also from the description of the question, you come up with a graph, and then you analyze the structure of the graph. And very much in terms of network science, the questions you ask, and I heard some very nice talk this morning from Jennifer, where she analyzes this, she tries to figure out communities and stuff like that. So the questions are asked in terms of the structure of the graph, and there is a lot of theory about that. The data science questions, as I see them, are more traditional signal processing, data processing questions. I don't know if you can distinguish, but there is a blob of blue here, and there are a few red dots. Okay, and this blob it looks like a blob, but because there are too many nodes, this comes out is a very small sample of a 4 million network kind of node. 4 million node network, and practically every node has the same type of behavior. That's why they are blue. But there are a few nodes that have a behavior that is different from the others. And the typical question that we ask is, can I figure out, well, this actually is a snapshot, and there would be now the next snapshot. And what we want is, before I get the next snapshot, I'll come back to the application, but before I get to the next snapshot, can I guess which of the blues are going to turn red? Okay, so that's the question. Okay, and you see that there are very few reds, so this is what's called usually an anomaly detection kind of a problem. Okay, you have a dominant behavior, and there is someone that is misbehaving, and I want to figure that out. So that's my distinction between the two. Okay, so let me go back to this example here. Yeah, and this example, just to contrast again the network science and formulate the question in terms of the structure. This is a data set. The question that was asked here is, look at the Florentine families. So that's the families in Florence in the 15th century. And the question these people asked was, why were the Medicis the dominant family? Why were they the ones that sponsored Michelangelo and all those people? Okay, they were not the richest family. They were not the people that had more palaces or whatever. But somehow they were the most influential. Okay, so now I don't have the name of the actual people that did this study, but what they did is, okay, so the question is, can I figure out why the Medicis were the most influential family in the 15th century? So their idea was, well, let's build a graph of the families. Here I think there are represented 17 or 18 of those families, Italian families from Florence. And the nodes are the families, so the Medicis are here, the Strozzi are there, and all the others. And they decided to build edges, to put edges between families if there was marriage between members of the family. Okay, and so the Medicis, someone in the Medicis married the Barbadori, and so there is an edge there. Okay, and the Strozzis and the Castellan, there is an edge there. And then they said, okay, now how do we answer our question? What is it in this structure that somehow puts the Medicis, gives the Medicis some special feature, some special characteristic? And what they said was, well, if the Albizzi want to make some deal with the Barbadori, okay, it's natural, and maybe in the 15th century that was even more natural than today, to go through some common knowledge, some people that the Albizzi know, some people that the Barbadori know. Well, if there are family ties, then you go through those family ties. And so if you consider any pair here, it turns out that most likely going from here to there, you are going through the Medicis. So the Medicis kind of sat in the middle of all these connections, and so maybe that explains why they were the most influential family. But the point here is that the answer is to the question is by analyzing the structure. And so there is this coefficient called in-between centrality, and if you compute that, you come up with a value for the matrices that is much higher than for the other. So they sit in between practically every pair of families. Okay, so that's network science, and that's not what I'm going to do. Now, another thing that I want also to contrast to data science is, okay, so we have a graph, and this actually is a graph of about 5,000 nodes. You can see the edges because the edges are very dim, but each of these, either blue or red, represents a node. This is the power grid for the Western Interconnect, which basically is the western part of the United States, and is the power grid at some level of very coarse level, because it has about 5,000 buses or power stations or generators, loads, things of that sort. And then there are the edges. Did I break the things? Not yet. Okay. Then there are edges that could represent transmission lines. Okay. And basically, what we did, what this is studying is and by the way, this data comes from Watts and Strogat's paper on small world effects, 1998, from Nature. They used this data. But anyway, you get the network structure, but we are not interested in looking at the structure of the network per se, but rather suppose that there is a failure in the network, and that failure causes other parts of the network to fail. And so assuming some dynamics of how the failure or recovery of the failures occur, okay, so you take a generator out or you bring a new generator, so it's like if you take it out, it means like a failure. If you bring it in, it means like healing kind of thing. So you have a dynamic process in this network. And then the question you ask is, if there is a failure occurring in some part of the network, and the rates at which these failures propagate, okay, or you recover from the failures, which part of the network is more prone to failure, to stay, as the process evolves, to fail, and so that's not a network structure, although of course builds on the network structure, depends a lot on the network structure, but this is a dynamical process on network. So I refer to that as network process dynamics. And so failures, epidemics, so if you have viral propagation, or if you have fed, someone gets the iPhone 6, and then the friends get the iPhone 6 or whatever, so how does that fed propagate? So what this is showing is that if you let this process propagate for many, many iterations, then for the particular parameters that we assumed and so forth, you get these blues as being the parts of the network that are most sensitive or that most likely will stay failed after the process evolves. And depending on the parameters, you could get some other picture. So in this case, clearly the failure rate is much higher, the recovery rate is very small, and so this could be the onsetting of some kind of a blackout in the network. So this is another aspect, another very important aspect of this theory of having data supported on graphs or phenomena supported on graphs, on a graph-based structure, and you are trying to analyze the onsetting of, say, of failures in this case, and trying to figure out which parts of the network are more sensitive. And so here you have an interplay of both dynamical processes. Dynamical processes are like in the old signals and systems, the linear systems, the dx dt equals ax plus bu, except now it's the network and it's the the way the nodes of the network interact among themselves. That causes the dynamics. And in this case, we are looking at the asymptotic behavior of that. So that I call the network process dynamics, not the data science, okay? And so you have the network science. I haven't yet talked about the data science. And I place this network process dynamics somehow in the middle here because it has an interplay of the network, underlying network structure, but it also has data floating around. The data here is very simple. It's either blue or red, and the blues propagating or the reds recovering. So, okay. But my talk is, most of my time is going to be on the data science. So let me get started on this data science. And just as an interesting observation, why data science is a nice name is because there is a lot of interest in the broad community, in the popular press and not so popular, the New York Times, the Wall Street Journal, all these, Forbes magazine, all of them, I wouldn't say every week, but every month they have some article on data science. So, okay, so if we can somehow figure what they mean, maybe if they mean something similar to what we do, maybe we should also take some credit for that. So anyway, the Harvard Business Review in 2012, so about 2 or 3 years ago, said, okay, you want to find a job? Call yourself a data scientist, okay? And actually, my more recent students, when they go and find a job, and then I call them and say, so what are you doing? Oh, I am a senior data scientist. Oh, okay. So that's the way to do it. Okay, so it's interesting because this term of data science actually is not really new. And I met the other guy the other day, Jeff Wu, and I was telling him, I didn't know him. So I was telling him, he asked me, what do you do? And I said, okay, he's not in the electrical engineering department, so I'm going to shine here. I'm going to say, now I do a lot of data science. And he turned to me and said, do you know how the term came about? And I said, well, I'm not sure, really. I invented it. You invented it? Oh, come on. Then I went on the web, on Wikipedia, of course, and there it is, his picture. And of course, I'm sure he was the one who went on the web and updated the page. But it's true. It's true. And actually, if you go back in history, the term has been used. But what's interesting is that in November 1997, so about, 16 or 18 years ago, something like that, he got the chair, the Carver Professorship at the University of Michigan. He was at Michigan at the time. And his inaugural lecture was Statistics equal Data Science. Now, statistics is a misnomer. He should have said signal processing equals data science. But anyway, it's interesting. So the term has some roots in history, and there is someone that can claim, of course, as you know, science is essentially a tautology. You keep repeating yourself and reinventing yourself. So he reinvented a term that others might claim before him, but at least he has, and by the way, he's now at Georgia Tech, and he's in industrial engineering or something. He's an operation research kind of a person. So anyway, let me tell you why there is suddenly so much interest in these things with data and so forth, and why. So when you talk about signal processing, usually you tend to think of physical-based signals, and although, of course, once they are digitized and put in the computer, who cares about the original source? But still, why is it that suddenly there is one of the things is that if you look at the way data has been collected over time, and if you go and by the way, this slide is not mine. The slide is from a guy called Mark Davis, and I heard him talk once, and I was fascinated. He does a much better job in explaining the slide than I can, but at least I can give you the idea. If you go and the place in this timeline here that goes from 1750 till today, you will have the several revolutions, the several industrial revolutions, okay? And you see that the data that each industrial revolution kind of span and the data collected and so forth kind of start going. So this is industrial revolution number 1. And it's like the steam engine, got the trains and all that. And the amount of data was very, very small. And then 100 years plus later, the second the combustion engine came along, electricity came along, water being pumped and distributed to the households and all that, and more data, but not much. Okay. Then again, this is at the end of the 19th century, say 1870, 1880, 1890. And then 100 years later or whatever, then you come to, now of course, is this a revolution or not? But since we are living, or some of us are living here and then here, we are going to claim that we are living through 2 revolutions, not just one, okay? So this revolution here with the computers, the networking and all that, and you see that now we are getting into the 100 terabyte kind of data produced annually and things of that sort. And then you come to more recent times, maybe 10 years ago or so, and with the robotics and with the internet and with the web and all sorts of other things that are happening, and you see that we are getting into this part here of the data generated. So let me now focus on that to get an idea. So as time goes, you started with data and you end with data, okay? And the data kind of gets bigger and bigger. And how big is big? Well, in terms of, it's not just the volume that gets bigger, but it's also the rate at which it's being produced, it's being generated. It's the variety. We were discussing the structured versus unstructured data. So it's a lot of V's. Actually, if you go on the web and you say big data, depending on the site you land, there will be 4 V's, 5 V's, 6 V's, 7 V's. I don't think you go beyond 7 V's. At least I couldn't. But anyway, I'll add, I don't have enough imagination for V, so I added the U and the D to the big data. Okay, so it's different. It's different from your time signals. It's different from your images, and it's different in many different sorts of ways. Okay. And now, how big is big? So there is this company that does these studies and says, okay, technology is going this way, and in 5 years this will happen, or 5 years that will happen. And so, again, in 2012, they say that by 2020, at that time was 8 years down the road, now it's 5 years down the road, at 2020, you'll have produced, created, replicated, consumed per year 44 ZBs. Okay? Just in case you don't know what a ZB is, it's simply 44,000 EBs. Oh, you don't know what an EB is? Okay, let's go down. 44 million PBs. And if PBs does not meet your fancy, I can't count the zeros anymore, but I think it's 44 billion TBs. And by the time we reach here, I think it's 44 trillion GBs. Now, GBs everybody knows, okay? Because gigabytes is what we eat for breakfast today, okay? In our, okay, so can you imagine the 44 with all these zeros plus 9 zeros? That makes 44 times 10 to the 21 per year. Remember, this is per year. Every year we produce that. Okay, that's difficult. So I said, okay, I can't tell you what this is, and you don't know really what it is, so I went to a different unit. So I came up with the unit, not me, someone else. This is a unit some people use, which is an LOC. Okay, it's like a kilo or cubic meter, whatever, for data, an LOC. Okay? And 44 ZBs are simply 170 million US LOCs. Now, what is an LOC? Any guess what's an LOC? I'll help you. It's located in Washington, and it's called the Library of Congress. Okay? So people, to kind of measure the complexity or the amount of data that is being produced, start saying, okay, what is the largest thing that we can think of as humans? Well, okay, there might be other measures, but the Library of Congress is a big repository of data.
To be
Okay.
distinguished from Congress.
Hmm?
To be distinguished
from Congress.
Unlimited.
That's right. Okay. And so this is not just every book that is ever published, at least that there is a copy in the US, as every map, every image that the Library of Congress has, every video, every CD, everything. They kind of computed the amount of digital data that if they digitized all that would correspond to. And so that's big, but actually per year you will be producing 170 million such amounts of data. Okay, so the LOC is no longer a big number. That's what this is saying. So there is a lot of data. Okay, let me now start contrasting the data that is being created from the data that we used to think about. And of course, we think about a lot of time signals, different origins, images. So at least this one I think I got right? I got this one right. And images of different types. And this should be a video, but I'm not going to show it because it doesn't show well, and also it takes forever to launch. So, but this is the type of signals that we have been working on, the type of data that we have been working with. Now, what's the type of data that, besides that type of data, now is contributing to those 44 ZBs? By the way, the 44 ZBs, it's interesting because I compute the rate at which it doubles every 18 months. So that follows Moore's law, right? Moore's law is 18 months. So it follows exactly the data, the rate at which the data grows is that. So examples of data that we may be interested is, for example, customers of a service provider, in this case a wireless service provider, okay? And you see Verizon, I think, has about 400 million customers. Between the wireless and the landline customers, they have about 400 million. So it would be a network with 400 million nodes, for example, okay? And each creates a lot of data. This one is a very different one. These are blogs that are hyperlinked on the web, okay? And so the blogs, for example, are nodes of the network. The links, the hyperlinks can be the edges of your network. Here the signal is simply a very simple signal. It's the color representing the tendencies, the opinions, the tendency of the opinions that each blogger expresses. Okay, we'll come back to that. Here is, for example, a social network from LinkedIn. Here is a sensor network spanning the whole US, and it's a weather. Each node is like weather stations, and maybe the edges represent some association between the weather in one place and the weather in the other place. And here are, for example, friendship networks, and this, of course, is the internet. So it's analyzing systems like this, no longer just the dynamical systems that we study in signals and systems, x dot equals ax, but systems where the network itself is very important. And the data is supported by this graph, this network. So that's this type. And the reason why we say this is unstructured is, of course, because if this is not, why is this node 1 and that node 2? Okay, and how do you really relate these nodes or the data supported in these nodes? We'll come back to that. Okay, so another type of data that For example, I have a student working with this type of data. So just to say it's a lot of data. 750 million records of taxi rides in New York City were recently placed on the web, so they are open data. This is for a 4-year span, so it's for 2009, 10, 11, 12, or maybe 10, 11, 12, 13, so those 4 years. And it's every taxi ride, yellow cab, medallion cabs, in New York City. And by New York City, it's not just Manhattan, but actually the 5 boroughs of New York, okay? And each of those records has the timestamp of start and geolocation by GPS, the duration, fare paid, tax, blah, blah, blah. Has all this information. So what do you do with this? It's an example of a large data set, not huge, but still it's about 50 or 60 gigabytes of data that you have available for you to study. I mentioned the Verizon. The healthcare, of course, is a big source of data. So these are our applications. Okay, let me quickly go through approaches that people has been developing over the years on this type of data. And so one thing is trying to do inference on data. Okay, so the data evolves over time, and you try to do your usual common questions of trying to infer. I observed up to here. What can I predict into the future? Or if my noise is data, if my data is noisy, how can I better extract the signal component of the data? And that has been a lot of work. I won't go through that. A lot of distributed optimization work. Okay. You don't want, so you have the data being collected in many different places. You want to do some global optimization without shipping all the data to a central location. How do you do that? So distributed optimization has done a lot there, but I won't go through that. Now, coming back to these graphical models, to this data based on graphical, so a lot of many in the machine learning community, so going back to our discussion over lunch, so machine learning has been doing a lot and using so-called Markov random fields. So they say that the data shows dependencies. Those dependencies are local, and basically what they say is that if I know the data at these boundaries, okay, if I have some boundaries here, then the data inside is kind of independent of the data from outside. Okay, so this is the generalization for these graph structures of the usual time dynamics, where I say, okay, if I came up to here today, I can forget about the past in terms of the future, because the state today plus whatever inputs I get into the future determine the future. So I can forget about the past. So generalizations of that go under the name of Markov random fields, and a lot of people worked on that. I myself did some work with a collaborator some years ago, and we looked at the traditional DSP kind of concepts, and we tried to generalize them to things that were not just time dependencies. But we made some assumptions there about the regularity of the graph. So the graph was like a lattice kind of thing, not an arbitrary graph. So we called that the algebraic signal processing at the time. And actually, what I'm going to talk about is how this generalizes to arbitrary graphs. Okay, so that's what I'll go about. So let me emphasize something here. When you have a time series, so here, this is a time series. So you have your sample times 0, 1, 2, 3, 4, and so forth. And you have the amplitude of your signal. Okay, so 0.5 to 3.6, whatever. Okay, and that's the signal you work with, and you don't think about anything else. Just okay, I have my samples at the different times. But actually, there is a lot of information that is implicitly assumed and that we take for granted, and we don't we think we don't use in our algorithms, and we use implicitly without ever thinking about it. And if you impose a graph structure to this data, now think of this as data. You don't know its time series. This is data, and there are some nodes in that data, and there should be some edges and so forth. Now, if you do that, the graph is actually a very simple graph. So the time samples are your nodes, the nodes of your graph, and the edges simply represent the successive nature. So this node succeeds that node because time 1 succeeds time 0, and time 2 succeeds time 1. And of course, if it's finite data, you have a problem at the end. And in this case, I simply assume that was like cyclic. You put your data around the circle, so you come back to the origin. But you could say something else at the end. Let's forget about that. But here you have a graph. Okay, we never think of time signals as based or related to graphs. But the fact is that the time series is actually supported by a graph, naturally by a graph, and the data is these sample values are simply now indexed not by the time samples, but let's index them by the nodes of the graph. So, say this value here, let's assume it was node 1, time 1, whatever it is, minus 0.1. Minus 0.1 is my data value indexed by this node here that, of course, in time means the sample time. Okay, so I'm associating time samples with the nodes of my graph. And I'm associating the edges with this very simple fact that one time n succeeds time n minus 1 and precedes time n plus 2. Okay, so the graph would mean that there is an arrow coming from n minus 1 to n and an arrow going from n to n plus 1. Okay, so there is a graph here that relates to that. And so the rest of my talk, what I'm going to do is I'm going to develop a signal processing or a data science for data that is indexed by nodes of a graph. But to make it very easy for you, what I'm going to do is I'm going to take this example, I'm going to capture in the context of this example the DSP tools that we learned, and some of them at least. Okay, so the big question is, how do I develop for data that is that unstructured data or data that is supported by an arbitrary graph? How do I define a signal, a graph signal? How do I define a filter? How do convolution? How do I shift the signal? Is there something like a Fourier transform for that? Is there a high-frequency signal, low-frequency signal? So these very basic concepts, except that the data is no longer time-based, but is arbitrarily based by nodes. Okay. So, so that's what. Just to mention some of the other literature. So people have been concerned with doing, for example, data transforms. So their motivation was very much something. So, for example, Tony Ortega, and some of the others here, they were very much interested in sensor networks where the sensors were placed at random places, so you were not sampling like a la Shannon uniformly sampling the data, but arbitrarily sampled, and so they wanted to develop ways of interpolating the data. And so they developed some things, and now you could establish relations between their work and what I'm going to talk about. Okay, so let me go. Yeah, sure.
So for a graph, it's two-dimensional, but you are converting it to the one-dimensional time series. And I'm wondering if there is some data loss.
No, there is no data loss. So the graph is whatever you have. You have nodes, and you connect the nodes by edges, right?
Right.
What I'm saying is, what is the graph interpretation of a time series? I'm giving you an example of a time series and going from the time series to the graph representation. In the time series, what I have is time 0, time 1, time 2. And I'm saying, instead of saying time 0, say node 0, node 1, node 2. It's exactly the same thing, okay? Except that instead of saying, when you say node 1, node 2, you don't really necessarily say that node 2 follows node 1, okay? But because we know that node 2 represents time 2, then we know time 2 succeeds time 1. And so what in the graph representation, I'm going to put an edge from node 1 to node 2, pointing to node 2. Okay, so that's all. It's like a different representation of the same thing. There is no loss of information. I give you the graph, and if I say these nodes represent time, you can construct a time series. If I give you the time series, you can construct the graph. Okay, so there is no. Yeah.
Why is it necessary to have that feedback? Are we trying to create a periodic signal?
Yeah, in this case it's for periodic signal. So if the data was not finite and was infinite, okay, then we would be concerned. Well, if it's infinite, then there is no problem. If it's finite, usually when you get towards the end, you need to worry about boundary conditions. In this case, I just say, okay, let's consider what's called cyclic DSP. Okay, and so your boundary condition is this. But you could, some other boundary conditions is to say that this equals that one, for example. Okay, so there are many ways of figuring out what happens towards the end, but let's not worry about that. Okay. So what I'm going to do is, as I said, I'm going to consider the old version. By old, I mean what we always learned in sophomore, junior level signal processing course. And then I'm going to provide the new interpretation, which is the graph interpretation. Okay. And once we go through 3 or 4 examples, then I'll say, okay, forget about everything, and now the graph is this arbitrary. Let's develop directly the concepts for graph. Okay. So the old is this time series, okay, and the new is superimposing a graph. Here what I'm saying is that time series versus some arbitrary data. Okay, I went through this. Okay, so the way we are going to do this, so DSP time signals, is usually in time we say, okay, my signal is S0, S1, S2, and so forth. Okay. Usually we give the signal as this. I'm going to represent the signal by vectors. So I'm going to stack all these samples into this vector. And then I'm going to consider linear DSP operations. Now, because linear DSP operations, because I now transform my signals into vectors, linear is going to be matrix vector multiplication. So everything that you did in your DSP class should be reinterpretable as matrix times vector. Okay, so when I'm going to talk about filters, you know, filters is usually impulse response of the filter convolved with the input signal. Because this is all finite, you can reshuffle everything and write as a matrix times a vector. Okay, so that's what I'm doing here. So what is the simplest filter that you have? Well, it turns out the simplest filter is Z minus 1. So you put your data, S0. Now, S0 is a bad example because that depends on the boundary condition. So let's look at S1. S1 comes in and gets delayed. So if it gets delayed, the output is going to be S0. So S1 gets to S0. Okay? Then Sn minus 1 gets delayed, so gets to be Sn minus 2. Okay? So this is the shift, is the simplest filter that you have. Okay, but this is a vector, this is a vector, this is a linear operation, so I should be able to write this vector as a matrix times this vector. Okay, that's what I mean by reinterpreting the usual DSP as matrix vector multiplication. And the matrix is a very nice matrix. It's this so-called cyclic shift. So it's zeros everywhere, and it has ones on this diagonal here, and there's a 1 there. This depends on the boundary conditions, so forget about that. But all these basically is telling you this is the input. So the input, when you multiply by the second line, okay, recovers the S0, so that's the S0. Okay, and as you go down the line, you get all these ones there. So this is the matrix representation of shift. Okay, trivial. Okay, input, shift, output. Okay, very good. So this is my shift matrix again. Now remember, I want to go to a graph representation. Okay. You stare at this matrix, and this is our zeros and ones. So we know that graphs usually are represented by matrices with zeros and ones. So what is the graph? Whose adjacency matrix is this? Well, when you go to graphs, you need to label the nodes. If this is going to be if this is representing a graph through what's called an adjacency matrix, you label rows and columns by the nodes. So this is node 0, 1, 2, 3, 1, 0, 1, 2, 3. And you parse each of these rows. And if there is a 1, then there is an edge between this node and that node. And so you do that, and there they are. So here are the nodes, V0, V1, V2. The V is for vertex, the vertices. So vertex 0, vertex 1, 0, 1. And now you have that particular one there, and that means the edge that goes from the Vn minus 1 to V0, okay? Goes from 0 to n minus 1. So, and you keep repeating that. So for example, that one gives rise to this one. And so this is what I told you, that we had this directed graph, okay, where the nodes are the sample points, okay? These are the time samples. These are the time samples, okay? And the arrows simply mean the precedence, one following the other or before the other, okay? So there is this, and the interesting thing is that I go from my time series to the graph representation through the shift operator, which you call it the adjacency matrix. Okay, so that's all there is. All the rest now is just working this idea. Okay, so here are examples. Let me skip these examples. So I'm going to call the graph shift the adjacency matrix of my graph. So if I have a graph, okay, if I have a graph with some adjacency matrix, I need to come up with a shift with that very simple filter that's called the shift. Well, just use your graph, just use your adjacency matrix. Okay, so now I'm going the other way around. I start with the graph. The graph has some data indexed by nodes of the graph, and the output of my shift is simply this weighted sum. Okay, simply this weighted sum. Okay, so in time, okay, here is my graph. Filters, I told you, is all interpreted as products of matrices by signals, by input signals. So in terms of graph filtering, same thing. You have S, the samples. But now remember that what labels the samples is the nodes of the graph. So it's this node, this node, this node. Okay? And you are filtering means multiplying by some matrix. Okay? That represents your linear filter. So that's what graph filtering is. Now, in linear systems, a very important class is the class of shift invariant. Shift invariant means I shift input, then I filter, I get some output. Or I filter first, and then I shift the output. And if the filter is shift invariant, doesn't matter which one you do, where you put the shift. You can switch the order. Shift first, filter then, or filter first and shift then. So let's assume also shift invariance. So if you do shift invariance, which is shift first, remember shift means multiplying by the shift matrix, which is the adjacency matrix. So shift first filter is the same thing as filter first shift. If you do that, it turns out that filters then become polynomials in the A, just like you do Z transform, Z representation of a filter in time. Okay, it's a polynomial in Z minus 1. So it becomes polynomials in A, and so your filters become polynomials in the shift, and the shift is the A. Okay? which means I cannot put here some arbitrary matrix. The matrix, if I'm doing filtering that is shift invariant, this matrix has to be some polynomial. And this is very nice because now if I want to design filters, and you know that sometimes we do want to design filters, what I need to design is what's the degree of my filter and what are these coefficients. Because I have the class of filters are polynomials in A. Yes?
So if you think of a filter as a multiplication by a matrix, and because convolution is, as you were saying, commutative, so how come multiplying, matrix A times matrix B is different from B times A? So there must be some subtlety here. Is it because you're talking about things that are basically periodic? Is that the subtlety?
No. It's shift invariance.
Okay.
Shift invariance.
So Toplin's matrices, is that the...
No, this is the key. So if you assume that you are going to do if you are going to replicate DSP for linear time invariant, okay, more than time invariant, shift invariant. Okay, if you assume shift invariance, which means if you go back to DSP, if you have a cascading of filters, you can switch their order, right? Doesn't matter if you use filter 1 and then filter 2, or if you use filter 2 and then filter 1.
All right, that's what I'm saying. Convolution is beautiful.
Yeah. So if you want to replicate that here, what that implies, because filters are matrices times vectors, what that implies is that the filters, these matrices, have to be polynomials in A. And so when you multiply a polynomial in A by another polynomial in A, you have A times A, and that is commutative. Okay, so that's the key thing. So granted that this is not a generic theory of linear filtering in graphs. This is a generic theory of shift invariant filters in graphs. Okay. Now there is so as I said, you can design these filters. You need the L and you need these, but the L actually we have an upper bound because of a result in linear algebra, which is Cayley-Hamilton, that tells you that you don't need to go very high in powers of A, but I won't go into that. Okay, so you can define Z transforms as A transforms, just replace Z minus 1 by A, and we can just keep going. By Cayley-Hamilton, you have that. Now, the important thing is the discrete Fourier transform. Okay, so notice I'm going to represent the discrete Fourier transform. So you have your samples, time samples, you have your frequency here, and usually you write the frequency, the discrete Fourier transform this way. Okay, I told you that you can represent everything by matrix times vectors. So you put all these exponentials in this nice matrix. This is called the DFT matrix of order n. So it's an n by n matrix. You have all these exponentials. And basically, you can rewrite this for all the s's, S0 up to Sn minus 1, as a product of the DFT with your. So now the question is, okay, but I told you that I wanted a graph equivalent of this. So how do I figure that out from the DFT? Okay, now it turns out that there is a very nice result, which tells you that the shift is diagonalizable by the DFT. So here you have the eigenvectors of this matrix. Here you have your eigenvalues. And here you have the inverse of this, which is just the conjugate transpose. Okay. It's very nice. So now I go back to my question of graph. So how do I define my graph Fourier transform? Well, I'll have a shift matrix, which is the adjacency matrix of the graph. I eigendecompose, okay? And the Fourier, the DFT is this one, is the inverse of the matrix of the eigenvectors. Okay, so there is all there is. Okay, so you do that. So your A is, this is for the time. The time is the DFT. When you get the generic A, of course, it's not going to be the discrete Fourier transform. It's going to, you drop the D. It's only the Fourier transform, okay? But that's what it is. Okay, so so that's what I'm saying here. And so you have your graph Fourier. So you have your adjacency matrix. You have the matrix of the eigenvectors, the eigenvalues, the inverse. This is the Fourier transform. Okay, that's the DFT matrix in time. That's the Fourier transform, the inverse of the matrix of the eigenvectors. And the Fourier transform is simply F times S, which means VI minus 1 times S, and everything. And now the only thing is the frequencies. Okay, here is the frequency response of a filter. You simply compute the polynomial that defines your filter on the eigenvalues, and you get that is your frequency response. It's perfect analog of the time domain. And someone mentioned the convolution theorem. It's interesting because let me just go here. So here it is. I'm trying to filter S by some filter. Okay, you go through the motions, and eventually you get by eigen decomposing the A matrix and manipulating things. What you get is you first Fourier transform the data, then you filter, which is multiplication by a diagonal matrix. So it's very easy, and then you inverse Fourier transform. So kind of the convolution in the frequency domain is filtering. Okay, the only problem with all this is that in the time domain, I don't have the time to go through all this, but in the time domain, the frequencies are real numbers, so totally ordered. So you know which one is the low frequency, which one is the high frequency. But now the frequencies are actually complex, are eigenvalues of some adjacency matrix, so they are not necessarily real valued. So you have a problem of defining low frequency versus high frequency, okay? So you need to be careful there, but there is a way to go, and I'll just skip that because I want to just illustrate this with one or two nice examples. So I want to, for example, in this example, these are political blogs. This is the data from Adamic and Glantz. Adamic used to be at Michigan. Now I think she's at Facebook, but either Facebook or Google. But I think she's at Facebook. And Glantz, I don't know where she is. Anyway, they looked at the 2004 election, Bush versus Kerry, and they looked at the 1,224 blogs, and the blogs themselves considered conservative or liberal. Conservative means blue, right? And liberal, no, it's the other way around. Liberal is blue, and conservative is red.
It's a nicer color.
Hmm?
Nicer color.
Nicer color, whatever. My problem is that in Europe, it's usually the opposite. So I'm always confused which one is which. But, or at least the red in Europe would be the liberal side or the more left side. Okay, so, but no, here is, so these are the blogs predominantly following Bush, say this predominantly following Kerry, but of course there are some blues follow some reds follow some blues. But here it's a very simple. You have a graph, very simple way of coming up with the graph, the nodes and the edges. And your signal is very simple also because it's a binary signal. It's either blue or red, and so you can convert that to 1 or -1, for example. And now the question is, can I come up with a Fourier interpretation of this? Okay, can I come up with a Fourier interpretation of this? And so we have the adjacency matrix. You do your eigen decomposition. Then your signal S is either 1 or -1. You find the Fourier transform of that, multiply by this V -1. You get your Fourier representation of your signal, which was -1 or +1, red or blue. And then you have to be careful in terms of reordering the frequencies. You reorder the frequencies according to a method I did not describe. So, and in that reordering, you'll have the low frequencies on the left, the high frequencies on the side, on the right, and you plot then this S, and you get the blue, okay? And that signal that is mostly blue connect to blue, mostly red connect to red, fits your intuition of being a low-pass signal, a graph low-pass signal, okay? And in the Fourier domain, there is a drop, a significant drop. Now let's play the following exercise. Let's go in to this network, and let's pick a few blues and turn them into red arbitrarily. And let's pick some reds and turn them into blue. So just to see what I'm doing, I just picked 20 nodes or 40 nodes from that, 20 blues, 20 reds. This is just for illustration purpose. And you arbitrarily pick a few blues and you turn them into reds, and you pick a few reds and you turn. And let's repeat the same exercise, okay? And if you repeat the same exercise, of course, you changed now your adjacency matrix here. No, sorry, not the adjacency matrix, but your signal now in terms of the nodes changed. You compute your Fourier, and you get this red one, okay? And clearly, the red one is not as low pass as the blue one, which means that fits the intuition, because now your signal switches back and forth switches more between blue and red than in this case. So there is more high frequency content there. So this fits the intuition there. The other thing we did was do some classification study. The classification study was to say, I only give you a few blues, I only give you a few reds, and now I want you to extrapolate for all the rest, okay? So we designed some classifier. I can't go through that, but it's essentially a filter. You filter your data through a suitably designed filter, and then you threshold the data, and then you plot, and you get very reasonable results. This is classification results, about 95%. This is Koifman is someone who did another classifier based also on some graph theory that he introduced. And this here is the percentage of blues or reds that you give to the designer. So it's like when you are designing your classifier, you need some training data. So you don't need too much training data for this graph, DSP graph-based approach to actually get about 95% of the results. Okay. I think I'm running out of time. Let me just give you, this is for the customers of a service provider. Can you see red dots here? Or
yeah, they can.
Okay. Okay. So you have very few red dots, and then you have the blue dots. Question is, this is data that gives usage of these cell phone users over a period of 12 months. So we were given that data. We designed a classifier, and the question is, if I'm given everybody that drops the service, say, in the month of January, can I, from the remaining users, can I kind of guess who is going to drop service in February? Okay, so I have the red dots in January. I have the blue dots in January. I know that in February the red dots are gone because they dropped the service. But some of the blues are going to turn into reds. Okay, so the question is, can you, using the network structure, can you kind of figure out which blues turn red? So that's, and again, if you design taking into consideration the network structure is what's significant now, you can come up with a classifier for which this point is relatively good, okay? Because it has a very low false alarm rate. Remember, false alarm rate is what you multiply the blues. The false alarm rate corresponds to blues that you say are going to turn red. Because there are too many blues, you don't want a high false alarm rate, because then you are saying every blue turns red. That identifies all the ones that actually turn red, but gives you too many that don't turn red. Okay, so you don't want this to be high. On the other hand, you'd like to have here, this is probability of correct detection. From those blues that are going to turn red, you really would like to know which ones are going to turn red. So you'd like to get 100% of the blues that turn red and 0% of the blues that do not turn red, that you identify as red. So you want some point here. So we figured this point here is reasonable. Again, I'm not explaining to you how we got the classifier, but I'm telling you that by working with the structure of the graph, that helps you do that. I had many more slides where I could give you other examples, but I think I gave you the basic idea. And the basic idea is this. When you talk to people and they look at this data coming from these different applications, very often they tend to say this data is unstructured. What I'm claiming is that, well, it's unstructured till the moment that you build a graph. If you can build a graph, then you have the right structure to analyze the signals. And it turns out that things are not very different than from what we used to do, and you can define a spectral analysis and so forth, because what plays the role of shift in the traditional DSP is played now by this shift that is represented by the adjacency matrix of the graph. Everything follows through. Thank you.
We have time for just 2 quick questions. Any questions? We're a little bit over time. Any questions? Okay, I do have one question. So, I guess obviously you didn't have time to go into the details, but in terms of algorithms, do you transport basically the complexity or the simplicity, I should say, of the usual signal processing, like FFT and all that, directly to the graph structure, or
so
what's the cost? Is the question.
It's a lot. The cost is finding the eigenvalues and eigenvectors of the matrix. So theoretically, that's the potential. So in terms of the traditional thing, in terms of the traditional DSP, so if you go to an arbitrary graph, the question is going to be how do you find, how do you have fast algorithms to do the eigen decomposition of the matrix, okay? And of course, that's an n-cube type problem, where n is the dimension, except that the matrices are highly sparse. So if you start enlarging the data sets, okay, if you start enlarging the data sets, you have 2 approaches. Either you can't have questions as detailed as we used to have, that, for example, find me the spectrum over all frequencies. Okay? No, find me the spectrum over the 3 most important components of the spectrum. So you have to compromise there. That's one. Now the other is, if you insist in working with an arbitrary graph, then you are stuck with the complexity of the graph. So the question now is, how can I structure the real graph with graphs that are compositions, components like tensor products or products. There are different types of products, and some of my slides would go over that. But products of component graphs. Okay, so you approximate the complex graph by, say, the Kronecker product of 2 smaller graphs. Okay, now once you do that, the complexity is brought down to the complexity of the smaller graphs. Okay, so if you could write an n by n adjacency matrix as the Kroneckers, for example, of 2 by n1 and n2, then the complexity now is order of n1 cube or order of n2 cube versus order of n1 times n2 cube. So those are the tricks that as we go to larger and larger data sets we need to play. But anything that is based on the traditional DSP of spectral analysis, convolution, and blah, 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 all that is kind of incurs, you don't have, the Fourier transform that I think about it is that you know what the DFT is. Okay, no more. If I ask the audience here, whoever did the eigen decomposition of the cyclic matrix, I'm pretty sure that maybe one person would raise their hand, right? Because it's given to us. We never realized that, okay? But you go to an arbitrary graph, that's the work you have to do. Or else do approximations. Now, DFTs or Fourier transforms is not the only way we do signal processing on graphs, okay? And then there are many other things one can do, and in that we can find fast algorithms and stuff like that, okay? So usually iterative type algorithms. But that's my answer to your question. Yeah, Dan.
In traditional Fourier analysis, we also encounter complex frequencies, and in that case, the imaginary part we associate with stability somehow. That, I guess, implies some particular ordering in one of the domains. In this more general case, when you have complex frequencies, is there an interpretation of the imaginary part that's somehow analogous to that?
So I think so, but I haven't done it. So that's a very good question, to go back to the data and try to look at what is the real part of the eigenvalue giving you. So I would say most likely yes, but I have no idea. I can't, I mean, intuitively I have a similar idea, but I don't have some example that shows, yeah, look, stability is here. But I think. Now, since you asked for the frequency, it was quite puzzling to define this low pass versus high pass, okay? And that's another reason why DSP, traditionally on time, you take for granted so many things. If I can write, can I write on one of these boards? Here?
No, not with
No?
that one. You can write here.
With this one. Okay, so frequencies. So if you go to the adjacency matrix, you get as, oops, I don't think this writes. Okay, anyway, the frequencies, I think I have a slide here. I didn't have time to go through this. But it's actually quite interesting. I don't have the slides. So I don't know what happened to my slides. Maybe I can write here.
You can write with some of the markers on the
No, he can't.
I can, yeah. So anyway, so apparently I cannot write. Okay, so anyway, oh no, I can. Okay, so let me, yeah. So let me do here something. Okay, if you look at the eigenvalues of that matrix, the adjacency matrix, they are something like e to the minus j 2 pi over n times some k. Okay. Those are the eigenvalues of that adjacency matrix, which has ones on the lower diagonal and one there. Now, we don't call this the frequencies. What we call frequencies is this part here. Okay. And these are totally ordered. And so when we think of frequencies, we usually look, but that's the wrong concept of frequency, it turns out. The frequency should actually be this thing here. This is actually what the frequency is. Okay, except we, obviously in physics and in engineering and so forth, in time signals, we say this is the frequency. Wrong. This is the frequency. So when you go to graphs, okay, you are stuck with the eigenvalues. The eigenvalues are really what the frequencies are. Okay, and so that's another source of confusion. Okay, so anyway.
Yeah, that goes back to basically to the power spectral density of
Yeah.
the stochastic process. It's basically the amplitude, magnitudes of
Yeah,
spectral density.
exactly,
Yeah.
exactly. So anyway, this is so there are lots of connections, but once you go beyond our comfort zone of time series, time signals, we need to rethink. And ordering the frequencies, first we had to rethink what frequency is. So we were trying to do logs of lambdas. We couldn't get anywhere till we said, no, that's wrong. We have been using the wrong concept of frequency. This is the... Anyway, it's all questionable, right? Yes, please.
Yeah, so we know that the spectral graph theory is an important branch in graph theory, and the mathematicians have done a lot in spectral graph theory, like doing eigenvalue competitions on adjacency matrix and Laplacian matrices. It seems that if we take this adjacency matrix into this special form of the shaped matrix, then we kill the connection with the DSP. So in this sense, can we can we think of like this? What we do in DSP is actually a special case of spectral graph theory.
Yeah, that's what I'm saying. Now, the computer scientists, so in the early 2000s, people were looking at data reduction and spectral clustering and things like that. And they used the Laplacian. For those of you who know what the graph Laplacian is, the graph Laplacian, if you base your theory on the graph Laplacian, my reinterpretation of that is like doing a DSP where signals are autocorrelations. Okay? Because the graph Laplacian is a symmetric matrix, positive semi-definite. Okay? So it's the equivalent of doing, you just mentioned it, power spectral density signal process. The signals are all power spectral, not your arbitrary signals. So one needs to be careful there too. Okay.
All right. One last question. Okay. There was another question there. No? Yes.
So for all the examples we have seen are binary value examples, like either blue or red or positive 1, negative 1. So all this very good theory also applies to multiple value problems.
Yeah, it does. I only gave you these examples because these were the first ones that we worked out. But now we are working. The data is actually possibly even a time series. So each of these nodes is indexing a time series and how you do the analysis, but also using the spatial, let's call the graph the spatial dependency. Okay, the question really was, how do I take care of this spatial, this graph dependency? And what I'm telling you is just look at the adjacency matrix and build what you are used to working with this object, and then go to the vector, go to the time series, go to everything else. Yeah.
All right, let's thank our speaker again.
Thank you.
I was just wondering, could you then approach this sort of a random structure route